afternoon. Welcome to Next. I'm going to be talking about how to leverage AI on the cloud so that you can transform your business. I'm Valyappa Lakshmanan. Everyone calls me Lak. And this talk comes about after having talked to dozens of customers over the years in terms of basically answering a very simple question. All right, I'm hearing all of this hype about AI, but where do I actually use it? Right? What kinds of use cases come to mind? And typically the answer to this is you show them a laundry list of, here's a whole bunch of people who have used it. And what I've tried to do here is to kind of step back from that a little bit and come up with principles, right? The kinds of things that you see, the very broad areas. And we can basically look at it from a couple of perspectives. One way is I'll talk about how you see these in Google products. And I'll also talk about how we see these in terms of our customers' use cases. So when I talk about AI, and when you hear our AI, you probably think of things like Google Photos. You think of things like Smart Reply. These are incredibly buzzworthy. You hear about image models and sequence models. If you're a technical person, you think about convolutional neural networks and recurrent neural networks and LSTMs, etc. But when you talk about how do I use AI, I would encourage you to forget about all of that buzz. Because ultimately, what drives value in most companies is machine learning on structured data. Data that lives in a database. Data that lives in a data warehouse. Even at Google, right? And this is something that we did because it's possible to do because you can go through the entire Google code base and look at all of the models and see what kind of models are people using. And MLP is a multi-layer perceptron. It's essentially your standard neural network with nothing fancy in it, just having a few layers. That is 60% of all the models at Google. And this is the kind of model that you use if you have data that is just numeric and categorical, right? Just structured data. LSTMs are the kind of model that you use if you have time series data, or the kinds of models that you use if you have text data. Translation, text summarization, Smart Reply is an example of an LSTM model. That is another 30% of all the models at Google. So all of the buzzworthy image models that we hear about, that every tutorial talks about, that everybody puts on their slide to say, this is what you can do with AI, that's less than 5% of the models. Okay. So what do you focus on when you say, I want to use AI in my business? Structured data. Right? So that's the first thing to remember, is that the value actually comes from the data that you have in your data warehouse. So how do we use structured data for AI? And then, when we talk about buzz again, we talk about AI, and then we talk about machine learning, and machine learning is the part of AI that works today. So when we talk about what do we do, machine learning, right? So how do we use machine learning? It's essentially a way to use standard algorithms to get predictive insights from data to make repeated decisions. So let's kind of break that down a little bit. The first thing, of course, is that machine learning only works when you have data, and preferably lots and lots of it. So you have the data, but unlike the traditional, typical ways that you use your data, the difference here is that the algorithms that you apply to your data are standard. So whether you're a retail company, or you're an oil and gas company, or you're a media company, right? The way that you take your data, the algorithms that you apply are relatively standard. And that's basically what has driven this big use, this big growth in the applications of machine learning. It's a fact that the same kinds of models work across industries, work across verticals. So you apply these standard algorithms to the data, but those standard algorithms themselves aren't new either, right? When we talk about decision trees, or you talk about random forests, they've been around for a while, and those are what we mean by a standard algorithm. A decision tree is a standard algorithm that you can apply regardless of which industry you're in. But the key thing is that you apply these algorithms to data to create predictive insights. Normally, when we look at data, what are we doing? We're creating backward-looking insights. We're looking at your data, and you're saying, what happened? You're trying to understand what happened. Machine learning is about doing a predictive thing, right? Predicting something that happened. But that's not it. Until this point, I could be explaining everything that a business analyst does pretty much at every company. The big difference between what a human analyst does and what a machine does is this last bit. It's a repeated decision bit. The idea is that you don't apply machine learning if you need to make a decision once a year, if you need to make a decision once a month. That is not an ML use case. An ML use case is a decision that you make over and over again, many, many, many times a day. It's the kind of thing that you do every time a customer visits you. If you want to determine, is this shopping cart going to be abandoned? Now, that is a decision that you have to make for every customer who visits your web page. If you're trying to make a decision of, should I place my new store in this location, that is a decision that you may make 50 times a year. The 50 times a year decision is not a good candidate for machine learning. The thousands and millions of decisions a day, that is a great candidate for machine learning. And somewhere in between, you have to make a judgment call of whether this is a data analysis task or is it a machine learning task. So to give you an example of where this idea comes about, let me start with Google. So our flagship application is, of course, search. We're a search company. And the way search used to work a few years ago was that you would go into the search bar and you would type in the keyword Giants, and we had to show you either the San Francisco Giants, which is a baseball team, or the New York Giants, which is a football team. Which one did we show you first? Well, the way this used to work was that there was a rule base deep in the bowels of the search code that said if the query is Giants, and if the user is located in the Bay Area, show them results about San Francisco Giants. If the user is in New York, show them results about New York Giants. And if the user is somewhere else, show them results about tall people. Right? And that is basically the rule base for that one word, Giants. Imagine how complex the code base gets for every single thing that could have multiple meanings. So that's essentially the problem that you're facing, because we are writing hand-coded rules like this for each of these query phrases. And machine learning comes about because we say, this is a decision that we have to make over and over again, and we need to make it lots and lots of times. So how do we scale this so that we don't have to have someone basically create this rule for every single possible query term that could exist? And that's basically what prompted RankBrain, which is essentially a machine learning algorithm that started from this premise that, hey, when someone comes to our web page and they do a query, we show them a list of possible results, we know which of them they actually clicked on. So now we can train a machine learning model to basically predict what the best possible result ought to be for a specific query term. And we have enough examples of this. We don't have to go around and create separate rules for every one of the query terms. We basically have a machine learning model do this for us. So search is not purely machine learning. There are many, many, many signals that we use. But the machine learning signal turned out to basically create the kind of improvement that we see over 2 years of work, right? That one signal did. And that was amazing, right? And that basically was what prompted Google to sit up and say, man, this machine learning thing, it has legs, right? So what does that essentially say, right? So here's another example. This is of our customers. So Rolls-Royce, basically, I think you say Rolls-Royce and you think cars, but Rolls-Royce also does shipping. And they needed to basically interpret marine data sets. And again, the way they would do this was basically, it was a humongous data set. They needed lots and lots of rules, and those rules had to be crafted by hand. And they were basically able to create safety measures simply by basically, instead of doing these rule creation by hand, by basically taking those marine data sets and inferring what kind of actions ought to be taken, right, through machine learning. Okay? So the basic idea, the first premise here, how do you use AI? How do you use machine learning to leverage your business? Number one, look back into your business. Think about all the problems for which you are creating rules today, right? Any problem for which you're creating rules today, and you have been doing the good thing, which is every time you've made a rule-based decision, you basically have a data set that says, this is the information I used to basically, the information that went into your decision tree to do the rule, and the outcome, right? Was it actually correct or not? If you identified fraud using a bunch of rules, was this transaction actually fraudulent or was it not? So that's your label. And if you've been doing these rule-based, data-driven decisions for a period of time, that becomes your machine learning data set, and you can basically get out of this business of handcrafting rules and basically turn it over to a machine learning model, which can basically infer what the rules ought to be, and to do this in a more holistic way. So number one, how do you basically leverage AI in your cloud? Look at all your rule-based systems. Look at all your rule-based systems. Look at rule-based systems especially for which you have been collecting outcomes. If you've not been collecting the outcomes for the decisions that you're making, please start, right? Start saving whether those decisions actually worked out or didn't, and use those as basically the input to your machine learning models. So that's number one. So let's take a second use case. In this case, I'll be using Google Maps to illustrate the machine learning journey, right? The journey of a company that's basically going through this machine learning transformation. So I use Google Maps all the time, and I live somewhere in the south of that diagram, and I work in Google Kirkland, in the north part of the diagram, and every day I look at maps, and Maps gives me a route to get from home to work. Right? So great. And I can look at that, but is that machine learning? And you could say, well, I told Google where I live, I told Google where I work, and this is basically the route. And going from A to B, this is Dijkstra's algorithm. This is the A-star algorithm. We teach it in undergraduate computer science classes. It's a deterministic algorithm. So it's not machine learning, right? Going from A to B is not machine learning. Sure, it is essentially a deterministic rule. It's a rule that you can write down on paper and do it. How about this? So I was in Japan, and I was in a subway station called Roppongi, and Google Maps essentially told me that you're on floor number 2 of Roppongi Station, and to basically get to Google Japan, this is a route that you have to take. How does Google Maps know that I'm on floor number 2 of the subway station? GPS, this is underground. I'm not going to get altitude out of it. So at that point, the only way to know where I am is to basically use a whole bunch of other data sources. But the point is, to get to that stage where you're now thinking about how do I figure out where the user is from a variety of different data sources, you have to have solved problem number 1, which is how to get from A to B. Right? That is the core of your business. Right? Basically provide navigation information from A to B, and then you're basically then saying, okay, now how do I use data? How do I use ML models? Basically improve that experience. And that's what that second bit is. It's about improving the core business experience that you do with number 1. Right? And then you get the icing on the cake, which is I'm looking at a Google Now card. I said, this is where I am. What can I do in between meetings? And I was able to suggest to me that I should go look at the Suntory Museum of Art, which has the kind of paintings that I like. Now, if you're a sports fan, it might have probably suggested to you a sumo wrestling match close by, right? But the point being that this is now completely personalized, and it's still in that same realm of location and location-based services and giving you that additional information, right? So this is basically the journey that enterprises go through with machine learning. You start with the core of your business that you typically solve and you have already solved, and then you look at how to basically address individual use cases of that experience, of that user experience in a better way. And then finally, you look about how do I basically reach that very long tail, right, of that very rare situations that we need to do very, very well in. Okay? So let me take another example of this. This is in the case of, again, talking about this journey to give you an idea of how this works. Let's say that we want to we're a media company, and we want to find the best time slot for a TV show, right? So how do we do this? Well, we might basically have data that says, okay, here's the age and the number of viewers of that particular age group who basically have viewed shows like this show before. And I have location information of people who have viewed this show in the past. And then based on the location information, based on the demographic, based on the desirability of that demographic, I would basically say, okay, we're going to take this new show, and it looks like 7:30 p.m. on Wednesday is the best time slot for this show, right? This is essentially your traditional data analysis. There's no machine learning here yet. But in order to do this, what data have you collected? You've basically collected a bunch of data around the demographics of people watching the show. You've basically found the genre of each of your different shows. You know where the location is of all of these people who've been watching these shows. So now, given all of this information, can we do the next thing, the second step of that journey? What's the second step of the journey? Let's build a movie recommendation system. We might say, like, okay, let's go ahead and say, let's build a movie recommendation system. And your first approach, right, the simple approach would be something like this. You would say, I want to recommend popular movies in the genre that this user likes. So if I have a user who's between 30 and 39 years old, he's male, makes between $50,000 and $100,000, and lives in South Korea, and over time, I know that this person has watched a like a romance, 2 comedies, followed by a romance, followed by a comedy, then my prediction algorithm might be, let me go ahead and find the genre that the user has watched most often. In this case, it's comedy. And then let me go find where they live, which is South Korea, and find the 5 most popular comedy movies in South Korea, and that is my movie recommendation for that user. Right? It's a pretty straightforward, rule-based algorithm that basically takes advantage of the data, right? But the thing is, it relies on the data that you already have, the structured data that you have of the history of things that the person has watched and something that you know about this particular user. How does this become machine learning? You flip this around. Notice that we have a model, I have data, and I have prediction. Instead, you start from the data. You don't start from this idea that I know what the model ought to be, and therefore I'm going to go to the data, I'm going to make my prediction. Instead, you start from the data. You say, what's my data? I have all the movies, and I have all of the ratings that every user has done of all of the movies. And then your model is, if I want to go ahead and do a prediction, I'm going to find all the similar movies across all the similar users using criteria like the user's current preference and their age and a variety of things. But notice here now, all those very hard boundaries of age, income, genre, right? None of those exist anymore, right? This is much more amorphous. It can basically take into account that people are not, you can't bin them. Instead, it's a very continuous range, and you're finding similarity measures. And that's basically what machine learning helps you do. It helps you basically take into account multiple factors and weight them appropriately. Okay? So this is essentially that journey that you go through from first basically taking a core problem, solving it with data, thinking about how to take that data and solve it with analytics, and then using that data and rethinking it in such a way that you can basically account for different factors. So in other words then, the second thing that you can do with machine learning, right, the second way that you leverage your business with machine learning is that this is how you personalize your applications. And this is how you basically reach the people who are unlike every other 30 to 39-year-old who lives in South Korea, right? You're able to find smaller groups of people that they're alike and give them much more targeted recommendations. So machine learning is about basically, mostly what we do when we do businesses is that we basically say, we're going to take the middle part of our distribution, and we're going to target everything towards the 80% of our users, right? And we're going to forget about the other 20% who do crazy things. But instead, what machine learning lets you do is that it lets you basically go walk down into that tail and basically for every user find similar users and be able to do recommendations for them. So to get to the third thing, I'll start with one of my favorite quotes about Andrew Ng. And Andrew Ng is, of course, a famous machine learning researcher, and you would think that he would be the one who would be all gung-ho about the latest advances in machine learning theory. But instead, Andrew says, it's not about the best algorithm. It's about who has the most data, right? Because that's the other thing that we have learned over and over again, is that the best machine learning algorithms are the ones that have access to more data than any other ones. Okay? So when you compare two algorithms, forget about what everybody tells you. If you have two products that essentially do the same thing, ask them what data was this trained on. If you have two image models, ask them what data was it trained on. And if one model was trained on more data and better data than the other one, it doesn't matter what the quality of the algorithm is, that data is basically going to control the quality of the result that you get. So inevitably, it's about the data, the quality of the data and the quantity of the data. So what does that have to do with the way we approach our data stewardship? Because everything starts with data management. If you think back about how you collect your data, and this is something that I'm now noticing now, is lots of times what we do is that we take our data and we aggregate it and we store it and we try to build algorithms, machine learning algorithms and data analysis tasks on the aggregated data. What do we mean by that? Instead of doing a machine learning on every individual transaction, you try to forecast sales by aggregating all the transactions over days and take the daily data and use it to predict sales. That doesn't work. Because what have you just done? You've taken this very rich data source that you have of every individual transaction that has ever happened, and you've thrown it all away, and you've kind of combined everything, and now you basically have a data set of 365 points, and you're trying to use that to predict sales. Stop. Don't train your model on 365 points. Go back to that original data where you had 18 million transactions. Okay. You need to train your models not on the filtered data, not on the aggregated data, but on the raw data, on the original data. Okay? So that's machine learning is about doing things on as much data as you can. Right? Don't aggregate things too early. Don't filter things too early. Don't throw away data too early. Okay? That doesn't mean that you shouldn't clean things up. You shouldn't make sure they're good quality. right? We're saying that try to get it to the point where you don't need to throw away data, that you don't need to aggregate this data to reduce the noise in it, that each individual transaction data has the right information that you need to build a better machine learning model. But it's not just about the data that you have. Also think about all the ancillary things that affect your business. So it's not just about the data that you have in your data warehouse. Think about weather data, think about traffic data, think about political events. All these things affect your business. So think about how to basically join your data sets with all these other diverse factors. And that is the data set that you should be using to build your machine learning models, to build your AI systems. And then, having now taken your data warehouse, considered all the third-party and partner information that you can join with, ask yourself a third question. What data could I be collecting that I'm not collecting today? Okay? Sensors are getting really cheap. There are something like 8 billion devices that came online last year. It's just an astounding number. And this is just connected devices. I'm not talking about devices that are not permanently connected. These are just connected devices. And it's getting to the point where data is ubiquitous and you can get it. The question is, are you collecting the data that actually impacts your business? So make sure that you have a data strategy that involves collecting this data from as many sources as you can, whether they're phones or they're IoT devices or whatever, and then think about how to basically take that big data that you now have, and what I mean here by big data is now the quantity of the data, unaggregated, unfiltered, the raw data, joined with everything else that affects you, with streaming data that's coming in. In the old days, like the 3 V's, in other words, volume, variety, and velocity, right? So that's basically what I mean here. And that's actually, when you think about it that way and you thoughtfully consider all of these things that affect it, it's changing businesses. Let's just take the first one, like games. 10 years ago, games were board games. Okay? Now games are essentially completely customized to the person playing it. Right? The characters that you encounter when you play a game are very different and have different skills than the character that somebody else encounters. And the only reason that that is possible is because of the amount of data that gaming companies are able to collect and how they're able to customize the game as you play the game. Right? And you see this over and over again as you walk down that list of companies that are getting completely transforming by rethinking the data that they're collecting and what they can do with the data. So as an example of another one, Schlumberger, who's one of GCP's customers, talking about how Cloud IoT Core allowed them to focus their engineering efforts to basically build reliable economic things, right? They're talking about 30 terabytes of petrochemical data that they can now use to build their models. So that's basically the scale that you should be thinking at. So the third aspect I want to leave you with is this idea that when you design your systems, design them with the expectation that next year you will have more data. Right? Don't start with this defeatist idea that the data that you have is all the data that you have today. Right? You will be able to get more data next year, and you want to basically work towards getting that more data, more diverse data, and build your models to account for that. Okay? So that's the third aspect of this design for more data, for unfiltered, unaggregated data. To get another idea of this, like talking about the kinds of devices and being able to connect them and basically create new businesses that just didn't exist a few years ago, right? Many of us use things like Philips Hue, right? Basically allows us to change the way lighting works. And now, right, Philips basically processes 25 million remote lighting commands a day. A thing that did not exist 3 years ago. Okay? And it's just possible because of all of these trends that are connecting together. Data, connected devices, the ability to basically train your models and basically deal with unstructured data like lighting commands. But this is all great, but what happens when you collect petabytes and exabytes of data? Oh. If you're going to be spending all your time doing provisioning, worrying about reliability, worrying about handling the growing scale, if you're going to be worrying about utilization, you're not going to be deriving value from any of this data. You're going to be spending all of your head count, okay, all of your human resources, all of your engineers are going to be basically just working on keeping this data up. And that's not what you want to be doing. You want to basically be deriving data, deriving value from it. You want to understand the data. And this is basically something that we at Google have a lot of experience with. And this is kind of why we've been basically building serverless data analysis, serverless ETL tools, serverless machine learning tools. Right? The reason that pretty much when you look at our data platform, everything is serverless, everything is a fully managed service, is simply because there is no way to do both things. There's no way to both have an engineer both be worried about, is the data going to be there when I need it, and being able to collect and basically being able to create models to derive value from that data. So, even though I think we started out talking about MapReduce and like the equivalent of these in 2004, we quickly realized that that cluster-centric way of thinking wasn't going to scale, and we basically moved on to things like Dataflow, which is open source as Apache Beam, right? To basically deal with this idea that you want to do serverless ETL, serverless extract, transform, load, build pipelines. So don't think of serverless as purely being around low-level functions. Serverless should be about your entire workflow. Your entire workflow needs to be serverless. And that's something that is the way that you basically manage petabytes and exabytes of data. If you've used BigQuery, you know exactly how we think about it, right? You write your SQL code and you don't worry about the thousands of slots that come up to basically execute those queries for you. That is how you should be thinking. You should be thinking in terms of code, not infrastructure. So, and this is something that, BigQuery is one of those things that people immediately get when they see it. And it drives a lot of transformation in a lot of our customers. AirAsia, for example, said, hey, we just need a platform that can scale to basically have our appetite for just this amazing growth in data that they're seeing. And BigQuery was ideal for that task. Right? So when you have this increasing volumes of data and you need to continue deriving value from it, think about fully managed serverless solutions. Don't settle for anything that involves you having to spin up a cluster. Okay. So the idea is spend time on what you need to do. Don't spend time on how to do it. Okay? So you focus on insight, not infrastructure. So another example of this is Blue Apron, who talks about after we moved to BigQuery, our query time was reduced exponentially, right? So they were able to do a lot more queries and, importantly, accelerate their decision making. Okay? An extra day is very, very, very valuable. Okay? And then, of course, the other question that we get is, but I have lots of data. Can I really stop managing all of this myself? And my favorite anecdote here is Evernote, because this is done by our professional services team, migrated 3.5 petabytes of content in just 70 days. Okay? So, and all of these are just very small documents owned by millions of users. And we're able to do that. And so it's definitely possible. You can move fast, and you can basically get out of this managing your infrastructure business. So, 4A, right? Use a platform that lets you forget about infrastructure. If there's a 4A, there's got to be a 4B. And what is that? So this is about the data part, but there's another bit that any cloud platform has to give you if you want to be successful in AI. and it is that you need flexibility. You need to have the ability to basically do your machine learning runtimes for different scenarios. For example, on Google Cloud, you can prototype with Cloud Data Lab or Deep Learning Image. You can do this prototype locally on your little laptop, and then run it on-prem with Kubeflow and migrate it over time to ML Engine. So it's giving you this for different scenarios. For example, if you have a device out in the field and you want to be able to run a model on that device, you want to make sure that your models are portable, such that you can train on the cloud, but do the prediction on the device out in the field. So you want to make sure that any system that you basically get and you run your machine learning runtimes on, they support all these different scenarios: training on the cloud, predicting on the device, training on the device, etc. Okay. The other thing to realize is that deep learning only works because our data sets are large. So the graph on the left basically talks about the training data size. This is for a specific problem, but different problems, we see the exact same thing. So for those of you in the back who can't quite see it, the x-axis is 2 part 20, 2 part 21, 2 part 22, etc. So each grid is a doubling of the data size. And each time your data size doubles, your error rate drops linearly. Okay, so remember that to drop your error rate by x, right, your data set basically has to go to a power of x. Right? Your data set doubles to get a linear improvement in error rate. So it only works, right? This drop in error, it happens with more data, but when we talk about more data, we're not talking 10% more data, we're not talking 20% more data, we're talking 1,000 times more data, 1,000,000 times more data, right? We're talking powers here, right? Lots and lots more data. So that's the one thing that we want to remember on the left-hand side. The right-hand side is the other scary part of the curve, which is these are the machine learning models, the state-of-the-art machine learning models. And the x-axis there is the year, and the y-axis is the compute capability that you need, petaflops per day of training. So AlexNet, which is on the way left-hand side, that is the thing that essentially started the deep learning revolution, is way down in the corner there. And again, the y-axis there is logarithmic. So every time a model goes up in that grid, the compute power is going 10 times, 100 times, 1,000 times. So now look at the compute power change in the last 6 years. From 10,000 on the top y-axis to 0.0001 on the bottom. In other words, right, your compute power that's needed to do state-of-the-art machine learning went up 10 million times in the last 6 years. Okay, I'll just let that settle in for a minute. Okay, the amount of data that you need doubles, 4 times, quadruples, right? It goes in powers. The data requirement goes in powers. The model requirement goes in powers. So you basically have 2 power laws going on. And this is kind of why your traditional chips architecture, Moore's law, they don't really work anymore. Right? This is the thing that our leadership saw 3 or 4 years ago that prompted us to start developing the TPUs. Right? Basically, this need to completely change the game in terms of what kind of data you need to handle and what kind of compute you need to be able to do this. So if you want to do machine learning, you need efficient, cost-effective places to do machine learning. Right? So when we offer that, we offer compute engine to which you can basically attach CPUs, GPUs, or TPUs. Kubeflow, which gives you this hybrid environment, and Kubernetes Engine, which gives you a great place to run it on Google Cloud, and Cloud ML Engine, which gives you a fully managed serverless way to use all of this hardware, and to basically do this in a distributed way. So the way you handle the increasing amounts of data is distribution, And the way you handle the increasing amounts of compute is better and better hardware chips. So you need distributed hardware chips. And that's basically what something like ML Engine gives you. It gives you distribution, and it gives you the best of the breed chips. You need both of those in order to do machine learning successfully. So, and the other thing to realize is that machine learning is moving towards increasing levels of ML abstraction. Sorry, you did not see the CNET. I guess it's CNET, so you already seen it. Okay, so let me just start with like 3 years ago what happened, right? Aucknet is a Japanese auction company. And they wanted to basically, they wanted to rethink the way car auctions work. The way it used to work was that you wanted to sell a car, and you would basically go fill out a form that said what car you had, how old was it, et cetera, et cetera, et cetera. Filling out a form, boring. So what Aucknet did was it said, oh, just go around your car, take a bunch of photographs of your car. Upload those photographs to our cloud, and we'll tell you how much your car is worth. Imagine the friction between filling out a form, take photos of your car. Right? Completely change the business. But in order to do that, they had to build a custom image model so they could price their cars. They had to do it. They had to write the TensorFlow code themselves. We helped them do it. They wrote it. It worked. They changed their business. Great. But I'm talking about increasing levels of abstraction. So Aucknet wrote TensorFlow code. Next level up, Ocado. Ocado is a UK grocer. They wanted to basically handle customer service emails. Right? The way it used to work was the customer sends an email, somebody at Ocado reads the email, says, oh, this customer is basically saying something about our produce. And then they forward to the produce department, and the person in the produce department reads it and decides what to do about it. It's a pretty wasteful process. So what did Ocado do? They used the natural language API. Google API, built on Google data, works out of the box, but it's not going to basically identify very specific things that are Ocado specific. But it's going to basically say the customer is happy, customer is not happy, they're talking about produce, etc. Right? And then Ocado has basically used that NLP API and then built a second model that basically said, if the NLP API gives you these tags, which department should you send it to? So in other words, they did not have to go to the raw text and build the complete model themselves. They could basically build off of the NLP API and build a smaller, easier model. Okay? That is that abstraction level that I'm talking about. You don't, as technology is improved, you increasingly don't have to go down to this level of dealing with raw images, raw text. You can basically build on top of existing APIs. Meanwhile, CNET wanted to basically have, it allows people to basically upload content, and sometimes people upload inappropriate content, right, for whatever reason. And so CNET wants to reject it, and they could reject it using the Vision API. Right? Straightforward, just use it as is. And then the next level up, Uniqlo, a Japanese retailer, basically they wanted to basically create a chatbot. And again, they don't need to go down to programming each of the individual words and what they mean in conversations. They could basically write intents. This is what a conversation is when somebody wants to find a matching blouse for their shirt, and the chatbot is basically able to take that and create a realistic experience for the user. Right? So you can think in terms of not very low-level LSTM models, but at very high level, what is the customer's intent? What is the typical transaction that they're going to walk through? And this is how you do it. So if you are doing ML, what does this mean to you? It means that you want to basically pick a framework that lets you do at every level of that abstraction hierarchy. You want to build a low-level TensorFlow model, completely custom, no problem. Use ML Engine. Right? If you want to basically use out-of-the-box models that they're basically trained on massive amounts of data, no problem. Use the Vision API, the Translate API, the Speech API. You have something somewhere in the middle. You want to basically take advantage of everything that the Vision API gives you, but customize it to your own things. Use AutoML. You heard in the keynote today that AutoML is no longer just about vision. We also have text classification in AutoML. The idea being we can basically build on top of Google here. So that is 4B. When you think about how do I do machine learning on the cloud, realize that machine learning, in spite of all the hype, is ultimately still software. And you want to make a buy versus build decision. And you want to make it based on quality, based on the kinds of things that you want to be able to do. So with that, we'll kind of summarize. What happened? Okay. So number one, machine learning can be used to solve many problems for which you're writing rules today. Number two, machine learning is how you personalize all your applications. This is how you reach the long tail. Number three, design your systems with this expectation that you'll have a lot more data next year. And number four, I've combined the A and B here, use a platform that lets you forget about infrastructure, that gives you a lot of great pre-built models. Thank you.